This is a video recording of the RRT algorithm for kinodynamic planning, trajectory planning for a car in a 2D plane. Now, it is not completed yet, but I wanted to show you the progress so far. So far, what we have here is we have a map, a 10 meter by 10 meter world. We have two obstacles here, which are just set between 4455 and 991010, which are described in this example map.txt over here. And we're starting from the screen node in 1.1 going to red at 7.7. And here's a script, and here you see the start and the goal. So that's why we do a hold on just to plot, and then we actually, most of the bulk of the logic is in RRT, and every time we're adding a new edge, we're plotting it. Every time we're adding a new node, we're adding it as well. So here in the first iteration, blue was a randomly sampled configuration, and we added an edge by iterating through all of the points in the tree to find the closest point. Now this is obviously, by the way, it's called Q closest. Closest Q. This is obviously the naive brute force approach, but if we're not planning to grow our tree extremely largely, then we should be okay. So as we continue, we'll see that it's sampling random points. There's no test on obstacles right now. So if a point gets placed over an obstacle, we don't do anything right now. Just because for now, I just want to get this to work without even having to worry about obstacles. Just, take it one step at a time. So as we continue stepping through, we basically see this connecting edges to all these points. And the end statement, which could take thousands of iterations, I have no idea, will be when the distance between the randomly sampled Q and the Q goal is less than some threshold. Now, obviously, this is not what we're going to do later on because, as described in the 2001 paper by Stephen Laval and James J. Kuffner called Randomized Kinodynamic Planning, it's a little more complicated where we have to take into the dynamics of the car. And basically, the main difference is here, as I press continue, it sampled this point right here. Let's call this X. Okay, so let's call this X. We sampled some new point X. This was called X near. And the way that the kinodynamic planning, as described, RRT described by Stephen Laval works, is we don't just connect an edge because obviously a car, if it's facing in like this orientation, for instance, down to left, it can't just get there. Additionally, car would not go straight line. And lastly, if we sample a point way out here, we can't expect that the same time step would get here versus here. So the way they get around this is by starting from this X near, you look over the whole map, find the closest X, and then you sample over maybe 100 different types of steering angles while keeping velocity constant at 1 meters per second, or whatever it's at. We'll say 1 meter per second. We sample it. So over 100, given the dynamic equation of the car, we know where the next configuration will be. It could be here, it could be here, it could be here, it could be here, etc. Once we have those, we keep track of which one has the minimum distance to this X that we wanted to get to, and that will be the point that we choose as X new. We connect an edge between X near and X new, and ideally draw as a little curve so it's a little more realistic. And that's essentially going to be what RRT will be. This will be modifications later that we currently do not have. But essentially, let's continue growing this tree, and this is currently, I don't know how many iterations. It's 15 is it 15 iterations? Yeah, because ij. I don't know why j is the same number of I, because that kind of defeats the whole purpose. Obviously, I'm doing something wrong here. Oh, no, because j grows up to I, so eventually gets there. But as we keep going, let's just see. I mean, right now, all we're saying is basically like, basically what I'm saying is continue choosing points until you choose one that's right next to this red dot within 0.1 meters and end, which obviously is not realistic. But let's just make sure it works. So I'll just keep pressing continue for now. Also, realistically, what it'll actually look like is more like the point you're at, if you can actually get there to a point near there, then end. Slightly different logic, but might be a bit faster. But let's just see how the tree grows just so we get a nice visual of what it looks like. Alright, I mean the chance of doing that, 10 times 10 is 100 square meters, and we're saying we want 0.1, so 0.1 divided by 100 is about 0.1%, I believe. So yeah. Alright, so let's keep going. So The reason I want it to end is so that we can then trace back the path. And maybe I should just do this by actually running it to completion one time. Let me see if that might work. The problem is that the hold off doesn't seem to work that well. But let's see. So I'm going to do a new one just because it's kind of pointless to type this so many times. So it doesn't plot yet. I think because it's going so fast, it's holding on and holding off. But once it's done, it should plot. We need to figure out how to get it to actually plot live. Let me write that down. Alright, so finish. Now this graph is such a pain to look at.
Are you talking to yourself or the translator?
Yeah, to myself.
Okay.
So we have all
Do
these
you have
points
a-
here. Wait.
Okay.
And then our path is going to look like, so if we want to see the path, here. So our path is only 8 points. Alright, so now if we can just like clear this or like draw some path in some thick line, that would be great. But essentially the path is going from 0, it's going from 1, 1 to 9, 4, which is wait, what? That doesn't make any sense. Wait, that is totally unrealistic. How can it go from 1, 1
Because you're bad at coding, that's why.
to 9, 4? So there's literally an edge from here to
You have
here.
your old essays?
Oh, I see, and it says blue line. Why is this path going that
You
far?
have your old
That
essays? Do you have your old essays?
Oh, you know why this
Do you
is
have your old
happening?
essays? Do you have your old
Because
essays?
this was
Hey,
probably
snap out of it!
Shut up. I'm sending this video. This is probably the closest path at like the first iteration. So obviously that's actually kind of bad. Because 1, 1 was actually the initial starting point. But it gets to 9, 4. We'll excuse that for now because we're not taking care of the X new logic. That takes into dynamics. Then it goes to 8, 6. So 8, 6 is up here. So the path base goes here to here to here. And then it goes to 7, 6, which is somewhere here. And then 7, 6, 7, 6, 7, 7. Okay, so basically goes here to here to here, here, here to there. And so the next steps that we need to implement. So first, it's good to visualize the path. But the main thing is that we just need to know where X new is relative to. Yeah, we need to take account of dynamics of the car now, which should not be too hard to do.